for the special case where the space that we're talking about is space-time, then the lines, the curves in space-time are world lines, right? And this will give you the curvature of the world line, all right? Now, so what does this mean? It means that in space-time, according to the equivalence principle, where we know that when you're in free fall, you don't feel any inertial forces, it feels as though you have no acceleration. That means that your covariant derivative of your velocity is zero. It's as though there's no change of your tangent as you drag it along with you through space-time. At each moment as you're falling in free fall, you feel that your tangent is the tangent to a straight line because it doesn't change. You don't feel any change in your velocity. You don't feel any acceleration. As far as you're concerned, this quantity is zero, which means that this will equal to this. Now, ordinarily we take this kind of a parameter that's not one of the coordinates, all right? In certain cases, you may end up finding that this parameter will be similar to one of the coordinates, and what we'll find is that the curved space-time equation boils down to something that has time over here, even though time is one of the coordinates. In other words, this parameter turns out to be very similar to time, and I'll show you in a minute why. I want to show you just a little bit of a sense of why this S turns into T. Back in the special relativity limit, in the limit of Newtonian kinds of speeds, the parameter that we're going to find here, which is really independent, it's kind of measuring lengths along the world line and so on and so forth, is going to be mostly dominated by time because it's multiplied by the factor of c. So this is going to end up being something like t. That's why you get an acceleration as opposed to just, okay, change it, let's say this will be r. Okay, and we'll see that in more detail later. What you're going to get, therefore, is this is going to be the acceleration. All right? And you're going to get plus some kind of a gamma. And we're going to find the specific gamma component that we spoke about last time. All right? If I wrote this here, gamma RTT, then this one is going to be dxt, dxt. What is dxt? What is dx1, dx2, dx3? What do they mean? I'll go over it again.
Derivatives of different components?
Of different components. dx1, let's say, could be r. dx2 could be theta. dx3 could be phi. dx4 could be t. All right? So this is going to be dx4, let's say, dx4. If I put t, I can just, instead of x4, I'll just call this t. Okay? And this parameter will turn out to be very similar to t in the special relativity limits. You're going to end up with dt, 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 dt. So basically, you're just going to be left with this gamma, this particular gamma. And you can end up with the covariant derivative of the velocity. In other words, what we expect as the acceleration is equal to a plus gamma, which means that this will equal to this. Now, so what does this mean? It means that in space-time, according to the equivalence principle, where we know that when you're in free fall, you don't feel any inertial forces, it feels as though you have no acceleration. That means that your covariant derivative of your velocity is zero. It's as though there's no change of your tangent as you drag it along with you through space-time. At each moment as you're falling in free fall, you feel that your tangent is the tangent to a straight line because it doesn't change. You don't feel any change in your velocity, you don't feel any acceleration. As far as you're concerned, this quantity is zero. So your A will be, and I'm not worrying about the signs here, A is equal to gamma or minus gamma, whatever. Okay? Your acceleration, instead of being zero in that case, usually a person describing motion without inertial forces, where they say my velocity is not changing, the tangent vector to my world line doesn't have any curvature associated with it. There's no second derivative. there's no first derivative of the velocity and so on, that means you have zero acceleration. But here, because space-time is warped, you end up having non-trivial connection, these gammas come in, and you end up with A equals gamma instead of A equals 0. This term is a new term that comes in because the time or the space-time is warped. Okay? So the acceleration is the connection. The gravitational acceleration is the connection in that sense.